I wanted a narrow straight edge to use on lathes. A 2-inch wide edge is ungainly to use on a 5/8 wide surface. I roughed out this one, which is 1 inch wide, 4 inches tall, and 48 inches long. However, as you can see here on its side, it ended up with a slight twist. Because the edge is 1/4 as wide as it is tall, the error on the edge will be 1/4 this, and could be scraped out. But I wanted to see if I could get the planer to do that instead.
But 1/1000 is small enough that it is difficult to correct with shims. This is a straight edge that I had previously done. After roughing the first side, it had a small bow and a bit of twist. As shown here, these are usually removed by using metal shims, placing them to support the part so that the downward tool pressure does not flex it. A bow or twist creates points of contact with the rest of the part arcing or tapering away from the table. Shim thicknesses are selected that will nearly fill these gaps, and then the shim is slid along the table toward the contact area until the shim becomes the correct thickness to support the part. The distance between the supports, whether shims or contact points, should be small enough that the part does not flex during cutting. Here you can see that the part is bowed, ends off the table, with one end slightly more so than the other. Notice that the shim in the upper part of the screen is a bit further along than the opposite shim. This is because that side of the end was a bit higher off the table. The amount of correction needed was enough that my shim collection could fit in the gaps. It is easier if the bow is large enough to allow for a variety of shim thicknesses and placement. For the larger straight edge that I'm working on now, I felt that the gap was too small to adequately support the part. One way to proceed would have been to shim the part to intentionally place a bow in it when clamped, machine the top flat, and when the part was flipped, it would have enough of a gap to shim and then machine it as I did the shortest straight edge. Instead, I'm going to try a different approach.
The problem is that in the weak axis, the part is like a piece of spaghetti, with its own weight easily able to distort it. Here it is supported only at its ends, and it has sagged about 10/1000 in the middle. And you can see what happens when mild weight is added. So if I place the straight edge on the table like that, it will tend to flatten out somewhat on its own. But if I place the supports 1/4 in from the ends, the sag is greatly reduced because the part is divided in two, with each half being supported at its middle. This means that the twist error that I showed is likely more than that. But it also means that the normal method of shimming between the part and the table to support it is limited. The thinnest shim I have is 1/1000, and so if I shim one end, the entire side is bridging between the shim and the other end. It will not reflect its at-rest state, and so after planing, the side will still not be flat. I came up with a plan which would begin by getting just one edge of one side straight. In essence, this would become a straight line that I will later use to define a plane. Then that plane will be copied to all others around the part. In the end, I'm not sure that what I did was worth the effort, but I wanted to see what the planer was capable of. To make my first straight line, I made a vise out of 4 slot blocks and 4 stop pins. As I already showed, by placing the straight edge on 4 shims, there is very little sag. Then, pressing the edge of the side that I wanted straight up against the slot blocks, I hoped to keep the part from moving as I planed that one strip straight. That strip will be the line. Pressing the straight edge up against the slot blocks will likely cause the straight edge to reflect any twist that is in that edge. But that will be ignored. I am trying to define a line, not a plane. That one strip will be used to define the plane of the opposite side. The part was flipped so that the strip was against the table, away from the slot blocks. Clamping this strip to the table ought to define the plane for the top surface. But since the top surface needed to be free for planing, the clamps would be temporary and will be removed before planing. Instead, again the part would be clamped horizontally in the vise. Now that I'm about to define the plane of the entire upper surface, I need to be sure that any twist that is in the 1-inch edge that is about to be pressed against the slot block does not twist the part. So I placed a 1/4 inch square halfway up the side to press against. This way the twist will remain so that it can be planed out. The clamps are tightened only slightly so that the strip will be held against the table, but its twist will not twist the part. To do the clamping, I use fingers to hold the part down and against the slot blocks. The fingers are positioned halfway up by a block against the table so that the forces go directly through the web. Once these fingers are in place, the clamps can be removed. What I hope for at this point is that the entire part will now conform to that one strip that I plane. Planing the 2 strips on the top ought to make a plane surface that I can then copy to the rest of it. Now the clamps can be removed. When I say copy, I mean that a plane has already been defined and I want to reproduce it somewhere else. Clamping to the table will make it conform to the table, and so any planing done on the top will be a copy of the bottom. And even if the table is not perfectly flat, since the planer planed itself, the table should be a copy of the tool path. That means when a surface is clamped to it, planing its opposite surface will make a copy of the first. Alternatively, a plane is defined by ensuring that the part is at rest and supported so that it will not sag or deflect from tool pressure when it is planed. This support is usually done with shims. Then, once defined, it can be copied. That's the principle. So now that we have a flat surface defined, the part is flipped, held against the table, and the bottom surface is copied to the top. Those 2 surfaces should then be flat and parallel. Note that I should have used 1/2-inch blocks under the fingers so that the forces traveled directly through the central web of the part. Those blocks that I intended to use can be seen in the lower right of the frame. I just forgot to use them. Fingers, or toe clamps, are used for holding down parts where the top surface must be kept clear and there is nothing for a strap clamp to purchase. Its base has a socket to fit the end of the stop screw. The other end tapers to an edge. In use, the narrow edge is supported off the table by a small block so that it is not against the extreme bottom edge of the part. The stop is raised so that the screw is higher than the narrow edge, so that when tightened there is a downward force to hold the part against the table. After tightening the screw, a hammer blow will force the part past the finger and against the table, and the finger will keep it there. Indicators are placed at clamp points to detect movement. I would like to see none. Once the fingers have been tightened, soft hammer blows force the part past the fingertips and down against the table. Then, the sound of hammer blows are used at various places to check that all surfaces are in contact with the table.
Now that the twist has been planed out and the two sides are parallel, let's see how well we did. Each of the corners are checked to see if they are resting on the table. I had no close-up of this, and so I shot this last corner later. The twist has been reduced from a little over a thousandths to a 10,000ths. At this point, I have finished trying to eliminate the twist, and have accepted that the result will be in the finished part.
Now for the critical edge surface. I could have placed the side directly on the table, but the T-slot placement was not optimal for cutting down the edge. So I placed it up off the table, supported at its ends by parallels. Then, because I do not want tool pressure to deflect the edge horizontally, I inserted parallels at the center as well. Then by placing a clamp there, I could prevent the horizontal deflection.
Here, by cutting down perpendicular to the plane that has just been created, the planer is cutting the all-important edge surface. This is partly another copy operation. By holding the part down against the table, we are copying that surface to the vertical side or edge surface. Therefore, any twist that still remains in the down-facing surface will be copied to the edge side. But it is also the defining of a plane in that the straight edge is at rest along its stiff axis. About 2/1000ths is being removed. This will make the surface even, so that the next and final cut will have an even tool pressure over the entire surface.
Incidentally, oftentimes when trying to eliminate twist, I begin like this, by cutting down the side, shim the widest part to eliminate the twist, and then make the cut on the edge. This allows the top surface to remain free and clamped wherever beneficial. Then, once the edge is straight, I could stand the part up and cut down the side, copying the edge to the side. A final 5/10 cut is made. Note that the DRO has a resolution of 5/10, and so moving the head a 5/10 change really means moving an unknown small amount. An indicator is used to check the edge just cut while it is still clamped. Now the edge needs to be checked while at rest. It is lightly held in place by a single clamp at the middle and aligned with the travel. Incidentally, an easy way to align a part is to clamp so that there is a known pivot. Then zero an indicator at that pivot and move the table so that the indicator is at the far end of the part.
Tapping the part to again zero the indicator will set the part into alignment. Note that this is a shot of an earlier attempt.
A tense indicator is used as the table is stroked. Since the edge is facing the same direction as when cut, we should expect little indicator movement. Several heights are checked to detect twist. Next, the edge is flipped so that it faces the opposite side of the planer. Any deviation should now be twice the planer's error. The edge seems pretty straight, facing this way too, so the edge is probably pretty good. With one edge now presumed straight and flat, I will refer to it as the original edge, and have marked it as edge 3. The original edge is copied to the opposite edge. Since it will be a copying cut, no effort is made to ensure that the part is at rest, and the true edge is merely clamped to the table so that its image will appear on the opposite edge. Since this edge is being flat-tooled, I will refer to it as either the flat-tooled edge or the copy. It will be marked as edge 4. The feed rate is low at 1/8 of an inch, so the tool pressure is lower. I want to be sure that high tool pressure does not cause inaccuracies for this test. This completes the cutting operations. Now it's time to see how well it came out, and we're going to use the planer itself to do this. As a first check to parallelism, the two ends and the middle are mic'd. As before, I'm going to use the planer itself to check the edge straightness, but this time using the table. First, with the original edge down, the straight edge is aligned reasonably well with the table travel. Downward pressure is applied to the ends and the middle. Next, the original edge is placed on the table in some random place and checked to see if it can be pressed down at either end or the middle. I have placed the straight edge at an angle so that the table surface is a combination of the stroke and the rail. Next, the straight edge is flipped so that the copied edge is down. I have marked the table so that I can place the straight edge in the same spot so that the table will be the same. That way I can presume that any difference in the measurement will be from the straight edge and not the table. Also, since the edge now against the table is a copy of the original edge, its error will be opposite that of the original because it has been flipped. The edges seem pretty good. In fact, I now suspect that my table is a little high in the middle.
Of course, the straight edge itself is exhibiting a slight sag, calculated at about 3/10 if the center is high, and half that if the center is proud. So because the center appears proud, the latter ought to be added to the indicator movement shown.
Again, if we lay the part on its side, we can use the planer stroke to see if it is straight that way.
Of course, like before, when the original edge faces the operator, it is reasonable to expect that the indicator will show straightness, because that is the same position in which the edge was cut.
But when the straight edge is flipped, so that edge now faces away from the operator, any error in planar travel should show up as double the actual planar error. Thus, it would be reasonable to assume from the test that the edge is at least as straight as half the indicator error difference between the two. But since I have not written down all the points, I'm just going to observe that it is pretty straight, in this case, within a few tenths. Doing the same to the copied edge increases confidence. And since the copy has been flat-tooled, its finish will be less bumpy for the indicator needle. Putting together all the checks, measurements made when the straight edge was standing upright agree reasonably well with those done when it was laying down. Of course, one hopes that the edge would somehow be perfectly straight. This seems pretty good. Certainly good enough to scrape.
Now that I've cautiously copied edge 3 to edge 4, I will be more cavalier and plunge the flat tool, recutting edge 4 for a better finish. With the tool spanning the entire surface, the roughness that occurs at the leading edge of the flat tool will be eliminated, and the finish ought to be better. Checking the edge, it can be seen that the ends are a little proud. Pondering this, I think that because there were no end stops, the ends were tightly clamped to the table to resist the broad cutting action, and this forced the ends down more than the middle. Recall that the edge straddled the T-slot with only 1/8 inch supporting it on each side, and that it was edge 3 that was down. Edge 3 was the roughest and perhaps the more collapsible. Trying a third time to flat tool this edge, I have placed end stops to absorb the cutting forces and 4 clamps to lightly hold the same original number 3 edge down against the table. I have plunged the tool 3 times, 5/10, 1/1000, and 5/10. This came out only slightly better, and it is questionable that the flat tooled edge is any better than the original edge. It will take almost no scraping at all to get below the machining marks, but that is not a great advantage.
Again, I am not sure that this process was worth the effort, but I thought that at least a few people might find this interesting. It was also something I could do without risking ruining someone's antique machine part by having a mental short circuit. In fact, I did have a crash that resulted in the straight edge becoming 18 thousandths narrower,